Bismillahirrahmanirrahim. Welcome to Network Analysis, and this is the episode number 10. And before going to proceed, I just want to again recap a little bit about the previous topic that we are discussing about the capacitance parameters, and that was completed with the help of even an example case in the last episode. So I think now it's the time to start the inductance parameters. Uh, Again, in the inductance parameters we will follow the circuit conceptual scheme, means that we will follow the basic three steps, that is the physical phenomena, field interpretation and circuit interpretation. Again, the physical phenomena very simple, where we discuss the quantitative manner and electrical phenomena which is observed by the experiment. But does it mean that the physical behavior can be seen, what we can see with our naked eye, what we can just imagine, and physical behavior without involvement of the formulas? In the next category we will define the parameters and the formulas that can be used, and in the last category we will apply all the important circuit parameters to relate voltage and current in place of the field relationship. So this is the overall story that we will again use in case of the inductance parameters. Formulas are a little bit different. So first let's discuss the first case, that is the physical phenomena. The physical phenomena basically tells us about this very very beautiful graph. Let us first discuss, graph I said. This is a box that tells us about the story of the previous first case, in case of the capacitance physical phenomena. In case of the capacitance, we discussed that if there is a charge, which just say a unit charge, that is if placed between the two charged bodies, like for example they are naturally charged or they are partially or charged, in any case, like there is a charge bodies, suppose opposite charge. But if there is a charge that is placed between them and it comes under the jurisdiction, it may experience a force like I draw here with the help of the arrows. So this unit charge can experience, and this is the case of the story. Will continue then in the stories was continued in the previous discussion, but in today's case it is the inductance. Now let's see how the story begins. According to the Wikipedia, the property of the electrical conductor or a circuit, like in case it is our mostly in circuits, we discuss in networks mostly circuits. The property of circuit that causes an electromotive force to be generated. So this is the actually inductance comes into the mind whenever whenever we discuss the induction of the electromotive force, means the induced something is produced or generated in a circuit, or in the form of EMF. Whenever a current is induced in a circuit, we will call it as EMF, not because to differentiate from the original current, this is the electromotive force EMF. Actually it is measured in volts, to be generated by the change in the current flowing. This is the source according to the Wikipedia. Okay. In 1820, a very important discovery, Professor Ørsted made an important discovery that there is a connection, there is basically a relation between the electricity and magnetism. What was the basically relation of the electricity and the force? We will discuss it with the help of the formulas from in the next coming lectures and in today's lecture also. But right now, this in 1820, very interesting phenomena happened by the class of the Professor Ørsted, when he see his compass that was actually very fine. He know about its all apparatus. His all apparatus is on the fine condition, and before he was before the turning on the connections of the circuit, he was just performing an experiment in front of the class to show something. He by chance see the compass was deflected from the north-south direction to another direction, new direction, when he turned on the circuit. And then he noticed that there is a relation between the magnetism and electricity, because due to this turning on of the circuit, means electricity is when goes through, charges goes through in the circuits, it it has something that wirelessly the it affects on the compass that is placed far apart from the circuit. So when turning off the circuit, it comes towards its original position, north south again. This is the our case, the force between the two charged substances. This is the force between the two charged substances depends actually upon our current, we simply say, or we can say in replacing the current, we can say the time rate of the flow of charge, that is also current. We can write it as the force depends upon time rate of the change of the charge, means the highest the charge flow with the limited time, the more will be the current. Actually the definition of the current is the rate of change of the charge with respect to time, so we can simply write it here as also the time rate of the flow of charge, but we can simple also write the current too. So we overall, it is the game of the current. If there is a higher current, like suppose I was just explaining the Urdu variant before the English variant lecture. So this was something. Suppose that there is a this is a wire and the current intensity is, for example, 5 ampere, and when 5 ampere there is an electric field around this, suppose electric field due to the current, and when the intensity is increased, for example 10 ampere say, then the intensity also due to 10 ampere increased. So this we can say that its jurisdiction is increased, its boundary is increased, which depends actually on the behavior of the or intensity of the charge. Okay, this was the first discovered by the Professor Oersted in 1820, and later on he received the prize also for this discovery. Later on in the same year, Ampere measured the force produced due to the current and expressed a relationship in equation form. That was a very important thing, because at that time Professor Oersted just showed that there is a relationship. He was just successful in this showing that there is a relationship. The needle of the compass was deflected by the presence of the current. So this was the only discovery that he was credited at that time, and still it is very important. The attention of the whole universe is diverged toward this, but at that time, later on, Ampere worked on that and finally developed a relationship equation. So Ampere measured the force caused by the current and expressed a relationship form, and then this magnetic effect is an action at a distance. Simply we can say action at a distance, because we are not actually touching with our hands to the to a point charge that is placed between the two things. We actually doesn't do anything, but still there is, due to the magnetic field that is present, there is a force on a conductor. Suppose this actually phenomena, when if you remember this phenomena, that here it is a two magnets north south, and there is a strong magnetic field between north and south pole magnets. And if we simply say that here it is this is our current carrying conductor. Suppose current is provided through external source, like with the help of the battery. Through external source this current is provided, and the current is now flowing, just suppose it. Then if the magnetic field lines are actually acting on the normal to the current carrying conductor, then the magnetic field will be magnetic force can be experienced either in this direction or in this direction, that makes an angle of 90 degree with the magnetic field. So there is an angle maximum at 90 degree. So this is the force that can be observed in case of the this was the later on relationship developed. Ampere's force law, this was Ampere's force law, states that there is an attractive or repulsion force between the two parallel wires carrying an electric current. So this was the first force law, Ampere's force law, that states that there is an attractive or repulsion force between the two parallel wires carrying an electric current. So if there is a first wire, say wire 1, and this was a wire 2, and the current is flowing, there is a strong electric field developed around the wires, and this electric field, if overlapping the other electric field of the second wire, there will be a force of attraction or repulsion that depends upon the magnitude and their intensity and the direction of actually the current flowing. So there is this is the basically Carl Ampere's force law that states different things and is very useful for our purpose. The magnetic effect is called an action at a distance, like same like as the case of the force between the two charged bodies. That was again the action at a distance. We are observing these from our naked eye and without any rocket science is needed to observe. This is the first step when we just need to take a look at the phenomenon, that what's going on, the scenario, and then later on we will discuss some important parameters and define the relationship about these things. The action at a distance is a basic observational fact which is not deducted from any knowledge, is not required. Simply we can just observe this and don't need someone if you have to call out an expert to check out what's going on with the circuit. This is the first step. Just keep calm, just observe that what you can catch with your eyes and from your brain without using any practice and calculations, because they are the steps too. So the next step coming on. If you see anything and track any activity in the first step, there is a second step. Go through and come here. In the previous discussion we observed that now we will discuss some formulas in this because we have some time. So I started the second point too, the field interpretation. The field interpretation, actually in the previous discussion we this discussion can be explained in terms of the force per unit magnetic pole. So this first we need to discuss that this is if we have north and south pole magnets, north south a bar magnet. The magnetic field lines for the conceptual purpose only can be drawn, and these are very useful because we can actually enhance our explanation skills and understanding skills if we draw these magnetic field lines. There is a north pole from where these all lines are coming outside, toward outside, and from this point these are coming outwards and then entering in the other end, that is the south. So the 2 points from where these lines are emerging and entering, these are the called poles. That are the actually sources. One is the source of receiving end, and then one is the as a source that is giving the magnetic field lines. This is the overall space where we can if we draw a point, we can observe and experience all the phenomena regarding to the magnetic field or magnetic pole. So in the field interpretation of the inductive parameter, we will discuss the force per unit magnetic pole. Like suppose I have a point here, force due to this magnetic effect per unit magnetic pole, means that actually we are interested in relating the relationship with the magnetic field lines. So this is actually the case that we are interested in the inductive parameters. So Oersted discovered that this force was directed at right angle to the current carrying conductor. This force that we are interested in the discussion, and this is the force that was directed at right angles to the current carrying conductor. Like if this is a current carrying conductor that we already discussed here, that if it is a current carrying conductor, this is a current carrying conductor, in a green color it is shown. Then also in 1820 Professor Oersted again observed that this force is directed at right angle. There is an angle, that is, for example, this is a conductor, current carrying conductor, current is flowing into this, and the force that we are observing makes an angle of the 90 degree. So this is the main thing that we want, and we use later on. Very important discovery. And I just draw this again diagram here, but this is we are not going to use this because we already discussed on the smooth law. And 1820 sorry in 1822, scientists Jean Baptiste Biot and Felix Savart, of scientists, their combined efforts after the discovery of the main discovery of the relationship between the electric field and the magnetic field relationship by Professor Oersted. These two scientists are succeeded in the defining an exact relationship between that describes the magnetic field generated by a constant electric current. The relationship for the first uh, thing that you need to keep in your mind while the limitation for this lies when you have a constant magnetic field current. You have a constant current, not a time with respect to time varying. And then this law is very important, just like as the law of Coulomb's law that was very important to describing the relationships about the charges and their force can be observed. But Coulomb's law was actually the law when the two charges are at rest. But this is the magnetostatics that this law has the same importance, and you can simply say the Coulomb's law was for the electrostatics, the charges at rest, while this law that we call that Biot-Savart law is used for discussion of the charges and the forces when actually the charges are in motion. So this equation is called Biot-Savart law. So let's go toward the final discussion. This is the actual variant of this law, where this is the magnetic field density and this is the integration sign here with respect to the distance parameter and the capacitance. We are not interested in these things right now, but only for the understanding. If this is a current carrying conductor I, there is a point P which is in the jurisdiction of this electromagnetic field that was due to this current. And if we have a point P here, we are experiencing maximum magnetic field here at the 90-degree, but force at 90-degree. This is the dB intensity can be observed magnetic field. We are interested in magnetic field density and B, and this micro or mu naught is the magnetic permeability of the atmosphere. Definitely it is different permeability, which is the function of the medium in which the magnetic field exists, and I is the current in amperes, and other quantities can be defined by using this figure. This is a P is actually the point, and DL is the parameter that you can see used in case of length parameter, that depends upon the length, and R is the parameter at some angle. This R can be used. So we will discuss this formula later on, but you don't need to remember this actual formula because we are interested in this case where it is free from the integration. Integral sign is removed. Then how we can remove the integral sign? If you can say, if first we will go through the back step here. If we want to remove the integration sign, we just need to go backward. Integration of the dB is actually the B. Like if we have the integration sign dB, we are integrating with respect to B, and then what happen if we integrate it? The answer is B, because there is actually the B raised to power 0. Then in the next step it is actually B raised to power 1 divided by 0 plus 1, and the overall our answer is B raised to power 1, which cannot be even written. It is understood. So answer is B. So if we are going toward the previous steps, we can replace the B with integral sign dB. Means that B can be replaced with integral dB. Integration sign is here and integration sign is here also. Both integration signs can be cancelled out. So the relation is dB is equals to mu I cos alpha dl. Cos alpha is definitely, you know, because this is a dot product, and it is always understood that cos alpha will be used, and we will discuss later on. And alpha is the angle, and I is the current in amperes. So these quantities determine the magnetic field at point P. All this relation is the magnetic field, actually density at point P, any point in the space. This is the formula that will be used for the circuit development theory and the circuit interpretation concepts. So keep this in mind, and we will discuss this in the next lecture. We will continue the discussion from this point, and then we will continue till the 20 minutes further, and let's discuss in the next episode further discussion and continue the lecture. So take care. Allah Hafiz.